One way of graphing a parametric curve is just to plot points and see if you can get some idea of what the result might look like. But there's another way that sometimes is helpful, and that is to eliminate the parameters. So this is an example that we have looked at before of this parametric curve, and we saw that this parametric curve actually traces out the line y equals 1/2 x minus 1. So where did this come from? Well, if you look at these two equations, it's almost as if this is a system of equations. And since we have two equations, we could combine them to eliminate one of the variables. And if we're thinking about, the graph of this parametric curve being a line in the xy plane, like this, this line, it doesn't explicitly involve t anywhere. So if we're going to choose a variable to eliminate, we would eliminate t. So let's see how that would work. We could take this first equation, solve it, so x equals 2t. Solve this equation for t just by dividing both sides by 2, and we get x over 2 equals t. But then we could take our second equation, y equals minus 1 plus t, and use this first equation to substitute for t. We would get y equals minus 1 plus x over 2. And here you see we've reproduced the equation of the line that this parametric curve traces out. So this is actually one way you can get a graph for a parametric equation, eliminate the parameter, and then you get an equation for a plane curve that you might recognize. Let's look at a couple examples. Okay, so let's sketch the graph of this parametric curve by eliminating the parameter. So we're going to have to solve one of these two equations for t, and I'd rather not use the quadratic formula. That sounds like it would be a mess. So let's take this first equation, x equals t plus 2, and solve that for t. So we can just subtract 2 from both sides. So t is x minus 2. Now we can take our second equation, y equals t squared plus 4t, and use the result of our first equation to eliminate t. So we get y equals x minus 2 squared plus 4t. I'm sorry, t is x minus 2. Then we should probably simplify this. So let's see, multiply everything out. X squared minus 4x plus 4 plus 4x minus 8. So that gives us y equals x squared. Let's see, it looks like all of these x's are going to cancel. X squared minus 4. And we know what that looks like. That's a parabola that crosses the y-axis at minus 4. And it looks like the x-intercepts here are going to be plus or minus 2. So something like this. I missed. There we go. So the parametric curve that we started with traces out this graph. Notice that by eliminating the parameter, this does give us a way to understand what path the parametric curve is tracing out. But since we eliminated the parameter, we don't actually know how the parametric curve traces this shape. Does it start up here and go down, or does it start over there and go to the right? We don't really know. If we needed to know how this was traced out, we'd have to go back to the original parametric equations and plug in some points. All right, let's look at another equation of eliminating the parameter. So x is 2 cosine t and y is 2 sine t. Now you might recognize, so for this particular example, there's kind of a couple different ways to do it. So let's do maybe the straightforward way first, which is let's just eliminate the parameter. It's hard to know which one to start with. Let's start with maybe x. So 1/2 x is cosine t. And so t is inverse cosine of 1/2 x. Then in the second equation, y equals 2 sine t, but t is inverse cosine of 1/2 x. Okay, and now we have this combination of a trig function with an inverse trig function inside of it. So remember, in this kind of situation, we can often do some simplifying just by drawing some sort of diagram. So remember, this inverse trig function, it produces an angle. We don't know what that angle is, so let's just give it an angle-like name. We can call it theta. We can draw a triangle that represents this situation, or draw a copy of the most important diagram that represents this situation. So let's see. Our angle theta is going to be here. For the cosine of theta to be 1/2 x, we would want this bottom side to be 1/2 x, and the hypotenuse to be 1. And that means that this right-hand side is going to be the square root of 1 minus 1/2 x squared. Okay, and now we can use this diagram to evaluate this sine function here. So y is 2 times sine of theta, which is, using the diagram, sine of theta is just the square root of 1 minus 1/2 x all squared, which is 1/4 x squared. Okay, so we get this equation, y equals 2 times the square root of 1 minus 1/4 x squared. This might not be something that you immediately recognize, but let's try squaring both sides of this. So if we square both sides of this equation, we get y squared equals 4 times 1 minus 1/4 x squared. Now this is starting to look like something I recognize. Let's distribute that 4. Y squared equals 4 minus x squared. And then move that move the x squared to the other side. You get x squared plus y squared equals 4. So this parametric curve that we started with, it was actually just a circle with radius 2, because 2 is the square root of 4. In fact, maybe that's something we should have noticed from the very beginning, because sine and cosine were sort of created for tracing out circles, right? If you look at this, the original parametric equations, it's as if we have x equals r cosine theta and y equals r sine theta, which does come from a circle. It's just, instead of theta, we have t, and instead of r, we have an actual number for our radius, which is 2, which was the radius of the circle that we ended up getting. So for this particular parametric curve, there was a shortcut that we could have used rather than eliminating the parameter.